There is a planet in our solar system where one side is being slowly incinerated by the sun, baked at temperatures hot enough to melt tin and lead, scorched by radiation so intense that the ground itself glows. And on the exact opposite side of that same planet, in the same moment, the temperature has plunged to minus 180 degrees Celsius, a cold so absolute it approaches the edge of what matter can survive. This is not two different worlds. This is one planet, and it sits closer to the sun than anything else in the solar system. The temperature swing on Mercury, from its blistering day side to its frozen night side, is the most extreme of any planet in the solar system. More than 600 degrees of difference, shifting from inferno to deep freeze within a single slow rotation. A world of endless fire, a world of eternal ice, both at the same time. Mercury is the innermost planet, the first rock from the Sun, orbiting at an average distance of just 57 million kilometers. To put that in context, Earth orbits at roughly 150 million kilometers. Mercury is more than twice as close to the Sun as we are, completing a full orbit in just 88 Earth days, racing around the Sun faster than any other planet in the solar system. It is also small, the smallest planet in the solar system, only slightly larger than our own moon. From space, it looks almost lunar, a battered gray, heavily cratered world with no color, no weather, no life. Nothing soft about it, nothing forgiving, just ancient rock and deep impact scars, sitting in the full glare of a sun that is almost 3 times brighter here than it appears from Earth. For most of history, the assumption was obvious. The closest planet to the Sun must be the hottest planet in the solar system. It seemed almost too logical to question. It is wrong. The hottest planet in the solar system is Venus, the second planet from the Sun, not the first. Venus maintains a surface temperature of around 475 degrees Celsius, day and night, pole to pole, without variation. Mercury, despite being far closer to the Sun, reaches only around 430 degrees on its day side, and that heat vanishes completely on the night side. The reason is simple, and it tells you everything about why atmosphere matters. Venus has one of the thickest atmospheres in the solar system, a crushing blanket of carbon dioxide that traps heat with extraordinary efficiency and holds it there permanently. Mercury has almost no atmosphere at all. What little gas clings to its surface is so thin, so sparse, so easily stripped away by solar wind that scientists call it an exosphere, barely deserving the name. Without an atmosphere, heat cannot be stored. The moment the sun dips below Mercury's horizon, the warmth bleeds away into space within hours, leaving the night side exposed to the cold of the outer solar system with nothing to slow the process. Mercury cannot hold heat. It can only receive it and lose it, endlessly, violently, with nothing in between. But on the day side, the receiving is extraordinary. Stand on Mercury's equator at solar noon, and the sun above you is not the gentle yellow disk visible from Earth. It is a monster, nearly 3 times larger in the sky, blazing with an intensity that no human technology would survive unshielded. The ground beneath your feet would be hot enough to instantly burn through any material you could stand on. The temperature of the rocks themselves reaches 430 degrees Celsius, above the melting point of tin, above the melting point of lead, sustained not for minutes but for weeks at a time as Mercury rotates with agonizing slowness. Mercury rotates so slowly that a single solar day, from one sunrise to the next, lasts 176 Earth days. The planet completes 2 full orbits of the Sun in the time it takes to rotate once relative to the Sun. This means the day side spends months under direct solar bombardment before the Terminator finally crawls across the landscape and brings the darkness. In that time, the surface rocks have absorbed everything the sun can deliver. There is no wind to carry heat away, no cloud cover to provide shade, no moisture to evaporate and cool the ground. The heat simply builds and builds, with nowhere to go. And then comes the night. As the sun disappears below Mercury's horizon, the temperature begins to fall immediately, not gradually, rapidly. Without an atmosphere to buffer the loss, the thermal energy that took months to accumulate radiates into space in a matter of hours. By the deep of the Mercurian night, the surface temperature has dropped to minus 180 degrees Celsius, colder than the surface of Mars, colder than the cloud tops of Jupiter, colder than almost anywhere else in the inner solar system. This is not a cold that simply requires a warm coat. This is the cold of space itself, pressed against bare rock, with nothing standing between the two. Water would not just freeze here, it would become as hard as iron. Carbon dioxide would solidify. Even some metals, at these temperatures, become brittle enough to shatter like glass. And yet, improbably, astonishingly, water ice exists on Mercury. Near Mercury's poles, there are craters, large ancient impact basins whose geometry is their salvation. Their rims are high enough, their floors deep enough, that the sun's light never reaches their interiors. Not at Mercury's oblique axial tilt. These craters exist in permanent shadow, untouched by sunlight for billions of years, maintaining temperatures that never rise above minus 170 degrees Celsius, even at their shallowest points. Inside those craters, water ice, confirmed by NASA's Messenger spacecraft, which detected hydrogen signatures consistent with water ice deposits in the permanently shadowed regions of Mercury's North Pole. Some of this ice may be covered by a thin layer of dark organic material, insulating it further. Some of it sits exposed at the surface, sitting in craters on the closest planet to the Sun, having survived for billions of years in the darkness. On Cosmic Vision, we explore worlds that defy every assumption, and Mercury defies more assumptions per square kilometer than perhaps any other world in the solar system. But something even stranger awaits on the surface itself. Imagine descending toward Mercury. The landscape that fills your view is ancient, among the oldest exposed surfaces in the solar system, a record of 4 billion years of bombardment, preserved with almost no geological modification. There is no wind erosion here. No water to carve valleys or smooth craters. The scars left by impacts billions of years ago look almost fresh, their edges still sharp, their floors still defined. The largest of these scars is the Caloris Basin, one of the biggest impact craters in the solar system, roughly 1,550 kilometers across, formed when an asteroid of extraordinary size struck Mercury early in the solar system's history. The impact was so violent that it sent shockwaves through the entire planet, and on the exact opposite side of Mercury from the impact site, those shockwaves converged, focusing their energy into a region of chaotic, broken terrain that scientists call the weird terrain. A scar on one side of a planet and a scar on the other from the same single impact. Across this landscape, you would also see the scarps, enormous cliff faces, some of them hundreds of kilometers long and up to 3 kilometers high, cutting across craters and plains in long curving lines. These are not the result of impacts, they are contraction features. As Mercury's interior cooled over billions of years, the planet shrank and its crust buckled and folded under the compression, creating these vast wrinkle ridges that wrap around the planet like the skin of a drying fruit. Only 2 spacecraft have ever successfully studied Mercury up close. Mariner 10 in 1974 and 1975 made 3 flybys of the planet and mapped roughly 45% of its surface. The first close-up images of a world that had been little more than a bright dot in telescopes for centuries. What Mariner 10 revealed was a landscape of extraordinary violence and age, but the mission left more than half the planet unseen and unmapped. It was not until 2011 that the Messenger spacecraft entered orbit around Mercury, the first spacecraft ever to do so, and spent 4 years conducting the most comprehensive survey of the planet ever attempted. Messenger confirmed the water ice. It mapped the entire surface. It measured the magnetic field, the composition of the crust, the structure of the exosphere, and it raised questions that no one had anticipated. Mercury's iron core is enormous, accounting for roughly 85% of the planet's radius. Proportionally, it is the largest core of any planet in the solar system. The mantle above it is thin, the crust thinner still. Why Mercury ended up with such a disproportionately large core is still not fully understood. The leading theories involve either a massive early collision that stripped away much of the original mantle, or unusual conditions during Mercury's formation that allowed the iron to concentrate in ways that did not occur elsewhere. The Bepi-Colombo mission, a joint ESA and JAXA spacecraft launched in 2018, is currently en route to Mercury and is expected to enter orbit in 2026. It carries instruments far more sophisticated than anything Messenger had, and its goal is to answer the questions Mercury's previous visitors left open. And those questions go deep. Mercury's magnetic field should not exist. At its size, with its slow rotation, the planet should be geologically dead, its core long since solidified, its dynamo long since stopped, and yet Mercury has a global magnetic field, weaker than Earth's but real, generated by a core that is, against all expectation, at least partially molten. How that core remains liquid when physics suggests it should have frozen billions of years ago is one of the great unsolved problems in planetary science. The solar radiation at Mercury's surface is something else entirely. Without an atmosphere to absorb or scatter it, the full spectrum of the sun's output strikes the surface directly. Ultraviolet, X-ray, particle radiation from the solar wind. Mercury sits so deep in the sun's gravity well that the solar wind itself is faster and denser here than anywhere else the planets travel. The surface is continuously bombarded, slowly eroded at the atomic level, its uppermost layer of rock churned and mixed by a process called space weathering that gives Mercury its characteristic dark, almost charcoal gray surface. It is a world being consumed, grain by the star it orbits. Mercury has no seasons, no weather, no atmosphere to speak of, no moons, nothing to soften the extremes it endures every single day of its existence. The searing heat of its long mornings, the annihilating cold of its long nights, the radiation hammering down from a sun that fills a third of its sky. And yet it persists. 4.5 billion years of fire and ice and impact and compression, and Mercury is still there, still racing around the sun on its tight, elliptical orbit, still generating its impossible magnetic field from its oversized molten core, still hiding its polar ice in the permanent shadow of ancient craters while the equatorial rock bakes at temperatures that would liquefy metal. We have barely touched it. 2 missions across 50 years, a surface mapped but not yet understood, a core that defies the models, a history written in craters and cliffs that we are only beginning to read. The smallest planet, the closest world, the one we know least, burning on one side, frozen on the other, turning slowly in the dark.